So now we will talk about uh, a couple of concepts that appear when you make an experiment. The first one is bias. The second one is variance. So bias is when you have differences that are caused by something else than the treatment you are interested in, and variance is related to the variability of the observations that you are having. Variance is very well managed by statistical tools. Bias, there is no way that a statistical tool can help you to identify bias or correct for it. Okay, so there are many ways of making bias. So, for instance, if you are interested in these kind of things and you're working in analytical research, this is an old paper, 1979, but it talks about 57 different kind of bias. So possible things that you that may cause differences in your measurements. And the best way of avoiding bias is randomization. So randomization ensures that each experimental unit has an equal probability of receiving a particular treatment. And you should always randomize using a computer, because if you try to randomize by hand, there has been studies that show that humans tend to make patterns on the randomized sequences. So yeah, this is a very simple way of randomizing using Excel. And randomizing can be done at the level of blocks. So let's say that you will perform your experiment in 4 blocks. So within each one of the blocks, you randomize, and then you apply treatments DACB and then ADBC. The treatments are in a random order, and within each block, all animals receive within a block that all treatments are applied to at least an animal. And blocking and randomization can be intertwined. So for instance, let's say that you think that there are a couple of variables that can affect your measurements. So you have sex and age, and whatever you're measuring may depend on sex and age. So you have 1,000 patients, and then 600 of them are males, 400 are females, and among the males you have this amount of young males and this amount of old males. So when you are at this point, you have very homogeneous groups. So you have young males, old males, young females, and old females. They don't need to be balanced. If they are balanced, it is better. But if they are not, that's fine too. So balancing or unbalancing affects the variability of some comparisons, and then once you are in an homogeneous group, you randomly assign to one of the treatment groups. So here, half of them will go to the new treatment, the other half will go to the current treatment, and then same for the others. And you see that in total, you will have half of the patients going to the new treatment, the other half going to the current treatment. And the allocation has been random, but random within the block. And one of the variables that causes more, or one of the factors that causes more bias is housing. So housing in animals, they can. Unfortunately, there is no clear answer about how. There is no single way of doing it, and there is not a right way. So there are several considerations. So for instance, single housing is stressful, and it is not recommended for welfare reasons, because these animals are social and they cannot live alone. But then if you put male mice, male animals in the same in the same cage, then depending on the strain and the husbandry, they may fight each other. So also you cannot put all the controls in one cage, because if there is some cage effect, then you don't know if the difference is because of the cage or because of the control treatment. And they have to be grouped, and also sometimes group housing. For instance, you put control and treatment into the same cage, but these animals are coprophagous, so they may interfere with each other. So you apply the drug to one animal, but then you see traces of that drug in the other animal. And sometimes you have animals that are single, in the sense that in each cage you have only one treatment and the others are companions. And you may do a couple of experiments together. So for instance, the 1, 2, 3, 4, 5 animals, they are receiving treatment, they participate in experiment 1, while the other ones participate in experiment 2. And there are ways, we will see this, for instance, Greek squares, where you can intermix these two sets of experiments in the same cage. Yeah, so there is no single right way of housing the animals. Blinding is also very important to avoid bias, because we always have an interest in the outcome of our experiments, and we might want to find significant differences between groups, or in some cases that there are no important differences. For instance, in toxicology, you want to show that there is no difference, and then once you have done the randomization, if possible, you should use animal numbers as codes to blind everyone to the treatment, so that the researcher doesn't know which treatment he's applying or he or she's evaluating. So this is particularly important when there are some subjective measurements, for instance, scoring histological sections or measuring behavior. And sometimes blinding is difficult because there are very obvious signs of what is the treatment, but as long as you can, you should be blind. And this kind of blinding can be at 3 different levels. So this applies more with patients rather than animals, but if the patient is blind, then that is a single blind. You have the double blind, in which the researcher doesn't know either the treatment, and you can also do a triple blind. So the triple blind is when the data analyst that he doesn't know, she doesn't know also neither the treatment that she is evaluating. So is randomization and blinding important? So for instance, here in this paper, they reported or they analyzed some other works about whether they had blinding, not blinding, randomization or not, or both, and they evaluated the odds ratio of declaring a positive or negative result. So if in blinding and randomization was not important, then these ratios should be around 1. But you see that they are far away from 1. So meaning that if you blind or not blind, if you don't blind, there is a 3 times more probability of declaring some results as positive, and the same for randomization. And if you don't do any of the two, these are 5 times more likely. So randomization and blind is really important. Okay, so the other important concept when you do an experiment is variance. So we would all like to have low variance, low bias experiments. So these ones here. So that means that, for instance, let's say that you have a difference between the control and treatment group, that is, let's say 5. And if you repeat your experiment, so you don't always get 5, but you get a very close number to 5. So you get 4.9, 5.1, 5.05. So you get very low variance. And if you compute the average of all these experiments, you get the true average, that is 5. You could have a different situation in which observations are much more variable, so the true difference is 5, but you repeat your experiments and sometimes you get 3, some other times you get 7. The average is still 5, so you compute the average of all those and still is 5, but it is much more difficult to detect your difference. And by averaging and having a larger sample size, high variance can be fought. And the opposite, the other concept that we have already seen is bias. So in bias, when you compare the difference between the control and treatment, what you see is that your difference is 3, but that's not true. The true difference is 5, but somehow you have some miscalibrated tool in your experiment or some other source of bias that makes you think that the difference is 3 when in reality it is 5. So this is a high bias, and you may have low variance. So meaning that every time you get a number around 3, and you could be in an even worse situation where you have bias, so you get 3 systematically, and you have high variation around these 3. So we would all like to be here and not certainly not to have bias. So variance is very much it is well handled by statistical tools. Bias, there is no way. Okay, so to reduce the variance, we have already seen one of the most important tools, that is these block designs or randomized block designs. So you try to identify variables that could affect your results, and then you make homogeneous groups within those groups. So for instance, here it was sex, so you have homogeneous groups of men, homogeneous groups of women, and then you randomly assign to each one of the treatments. And we will see later that by doing this block design, what you are doing is you are explaining part of the total variation of the numbers that you get in 3 parts. So the first part will be explained by the treatment, the second is explained by the blocks, and then there is an unexplained variance. And when you want to show that the treatment is useful, you have to compare the variance of the treatment to the variance of the unexplained part of your experiment. So the more variance you take away from the total variation by explaining them by blocks, the better for this comparison. Here you have another example of how to reduce variance and how to do randomized block design. So in this experiment we will block time. So for instance, let's say that you have to treat 20 female, 20 male, 20 treated animals, 20 untreated animals. And your experiment is such that you can only process 4 animals per day, and so you will need 10 days to do this experiment. So you plan to do the experiment in this way. So in the first week there are 5 days. Each day you will process 4 animals, but all of them are females and all of them are controls, while in the second week all of them are treatments and all of them are male. So if you see a difference between control and treatment, maybe caused by male female, so maybe the treatment is not doing any change, but the changes that you see are caused by male female. So this is an example of confounding that we were talking before. So now you are aware of that, and you organized in this way. So for instance, now you have treated females, treated males, and control females, control males. But if you pay attention, some of the days there are only males. Some other days there are only controls. And the number of controls and treatments and males and females within the days are not well balanced. And let's say that you have a shift in the animal house. So on Tuesdays, there are people who are different from those people on Monday. And then these people on Monday, they work differently and they are all treating controls. So maybe you have a small bias because of the people that are working on the animal house that day. So a much better design is one in which every day you have two controls, two treatments, and you have two males, two females, and they are intermixed. So you have a control, a female control and a male control, a female treatment and a male treatment, and within the days that are blocks, you have randomized your treatment order. Okay, so in general, this should be your mantra when you design an experiment. So you should control what you can, you should block what you cannot, and you should randomize the rest. So you can control typically the treatment, and you can block what you cannot. So for instance, sex, you cannot change the sex of an animal, but you can block it. And you should randomize everything else. So you should randomize position in the shelf, the order of feeding, the time of treatment, the order of treatment. There are people randomizing the person who applies the treatment, the pipettes used in the experiment. So they randomize absolutely everything. Here you have another interesting idea that we normally don't think of, that there might be external variables that we don't control, but that are affecting the observations, or the mean of the observations. This is bias, and they are also affecting variance. So for instance, in this example, they measured the weight of the animals when they were housed singly, so one animal per cage, two animals per cage, 4 and 8. And what we see is that the mean is different. So you see that when animals are alone, they can eat more, and not even more, but they can somehow, there are more variability. So when there are many animals per cage, somehow they control each other and they behave in a more similar way. So they eat less, and it is much more uniform. And you may not think of these things before doing your experiment, but this is just to highlight that there could be experimental conditions. This was the housing, but it can be whatever else that is affecting the variability and the mean of your observations. Here is another interesting idea. So you should choose subjects with the smallest variability, because that will give you statistical power. So if there is a difference, you will be able to detect it. And for that, inbred strains, they are very much used. So here you have, for instance, different names for different strains. So in this experiment, they wanted to see differences in the time that it takes to animals to awake from anesthesia. So they will anesthetize the animals, and then they will measure what is the time until they wake up again. And different strains, they metabolize the anesthetic in different ways. So the mean time to wake up is different. So you see that there can be very large differences. And the standard deviation are relatively small. So if you calculate what is the sample size that you need to detect a change of 4 minutes in the mean, when the variance are these ones, you will need 23, 7, 13 animals in each one of the groups, and you will have a relatively high power. And if you sum all of these animals, you have 79 animals in total. And if you use some other kind of animals, so for instance these outbred stocks, and these are two famous outbred stocks, then the mean values are these ones. The standard deviations are much bigger than these, so meaning that they have a smaller internal validity, and the number of animals to detect this change of 4 minutes is much larger, so even much larger than having all these animals in all these strains. We will come back to this slide later to explain it. Okay, so choosing an inbred strain is choosing a strain in which both alleles for each one of the genes are exactly the same. And if you have a different strain, then they have different versions of those genes. So that means that there is no genetic variability. All the animals that you're using from the same strain, they are absolute or complete twins, exact twins of each other. So if you make an experiment and you find a difference between these twins, can you say that this result can be extrapolated to the whole population? And not only that, probably the answer is no. And not only that, but these animals have problems to reproduce poorly. They are not good models for all genetic diseases, and yeah, they have a lot of problems. So there is another version of this, that is this hybrid F1 animals. So now they have, so let's say that you have two inbred strains, strain 1 and strain 2, and you mate them, then the offspring will have two versions of the genes for each one. So two versions of the two haplotypes for each one of the genes. So again, the different animals, all of them are the same, so there is no genetic variability, but they have gained something called hybrid vigor, so they reproduce better, they stand better diseases, and so on. Still, whatever you have found here can be extrapolated to the whole population. You have seen them, these results in twins, so probably they cannot be very much extrapolated. It is like, so let's say that you don't want to work with twins, but you want a small variability. So that is the outbred stock. So the outbred stock is working with animals that are much, so they don't have a very high genetic variability, although they are not twins. So it is like working in Laponia. So in Laponia, not many, there is not a lot of immigration in Laponia, and then all the people here, they are not twins, but they are somehow all related. The genetic variability that you find in there is not too high. So can it be extrapolated? What if you see a difference in some treatment? So can you extrapolate this to the whole humanity? Maybe not. And the other extreme of working with twins is working with mixed stocks. So mixed stocks, all animals are completely different. This is the total variation, genetic variation, and yeah, if you find a difference here, so probably that they can be extrapolated to the whole species. And so coming back to our experiment with the anesthesia, so working with twins, give you very low variability, so you need a small sample size, but you're working, if you work with a single strain, you're working with a single kind of twins. So it is what we show here with the 79 is that it is much better to work with different kind of twins. So the equivalent in humans would be working with Caucasians, or two Caucasian twins, working with two Asian twins, working with two Oceanian twins, and the same with black race, with whatever. So you work with in very controlled conditions, but you explore a variety of genetic background. So if you find a significant difference between two different anesthesia, then with many less animals you can detect these differences, and you can be sure that it can be extrapolated to a wider population, because you have seen this difference in multiple strains. So and this is much better than going to Laponia to make your experiment. And here is another interesting idea about variability, and these people here in this work, they very much worried about the reproducibility of their experiment. So they decided to make the same experiment in 3 different places, that are these 3, and they tried to do everything the same except the 3 places. So it was the same research team that moved to the 3 places. They were using the same inbred strains. They calibrated their apparatus the same way, same husbandry, same age, same everything. So everything that they could think of, they did it the same. And then they measured a couple of variables as the outcome of their results, and in some of the cases this is what you would expect, that there are no significant differences. This is the strain of the animals, so there are no significant differences between the 3 places. So you have done everything the same, so the results, there are not significantly different results. But this is not the case always, and you find situations in which there are significant differences, or very, very significant differences. So that means that still, even if you have tried to do everything the same, still there is something that you have not controlled, and that is making a difference between your groups. So that is why randomization and blinding are so important. So with this we finish this second block, and see you in the next video.